Good evening, everyone. I am Giovanni Tardini, computer engineer and IT director at EnergyWay. Today, I'm going to talk about dashboard visualization and analysis of remote sensing data, which is a task we often encounter in the rapidly shifting industrial landscape of these days. We're going to show you both a solution we developed in the context of an academic collaboration and an industrial one, both sharing the topic of gaseous masses. EnergyWay is a data science and artificial intelligence company who employs people from vastly different backgrounds. Here work mathematicians, computer engineers, neuroscientists, statisticians, physicists. Our approach is entirely based on data and technologies which allow to extract value from this data, allowing us to tackle a wide variety of problems in different industries, ranging from the sport industries to the financial industries, for instance. But let's get to the presentation topic. The problem under analysis is the determination of the age, actually the evolutionary timescales, of the I mass star formation process. What happens is that molecular clouds collapse under gravity and eventually form stars. Massive stars are the source of most of the heavy metals in the universe. And these metals are those that make life possible. If we want to better understand how life developed, then we need to know more about the formation process of these kind of stars. The problem of determining accurate evolutionary timescales for this process was approached in this case I'm bringing to you with a blend of chemical models and machine learning. Applied on spectral observations, you can see represented in the pictures on the right side, and the zoom in the small square. Tapping into the ATLAS-GAL database, we could access 110 sources with 4 different evolutionary classes, which became the training set for our models. In the current slide, you can see the machine learning pipeline which was set up for the process. The whole modeling process was optimized with grid search in order to find the best combination of feature scaling, latent vector embedding, and classifiers. Then, after the grid search process is over, the best combination of stages is further optimized with random search fine-tuning, improving the classification performance of the selected classifier. What is interesting about this pipeline is that, depending on the different techniques which get picked as best at every stage, we can immediately infer something about our data. For instance, if the standard scalar gets picked as best, we know that the majority of our features is Gaussian distributed. Also, if the best embedding is given by a PCA, then we can infer with enough confidence that the clusters determined by our classes are in pretty linear spaces. This kind of insight is extremely useful and valuable, and we decided to build a dashboard to visualize and interact with this kind of spectral observations. Here you can see the web dashboard which was developed. The idea is to give the astrophysicist a tool which allows him to quickly explore data which would otherwise be hard and cumbersome to plot. All this information comes from the ATLAS-GAL database, and we made it interactively filterable and explorable. Clicking on a source in the leftmost image, where you can see the white arrow, the whole dashboard instantly fills its plots and widgets with data taken from the clicked source. The images to the right show dust emissions at different wavelengths, and the table below shows information about the selected source. The 3 stripes in the central area correspond to the 3 main spectral surveys, which, in other words, constitute our dataset. The violin plots to the right of the slide show the distribution of the parameters of the sample. For instance, if we wanted an unbiased sample, we should cut off the peak of the 4th subsample, the red one, as it is exhibiting too high mass with respect to the other subsamples. Playing around with the sliders below the leftmost image, we can interactively filter the data, obtaining updated charts and information at every release of the slider. Then, after exploring the dataset, it is possible to switch to the Machine Learning Classification tab, before we were in the Data Selection tab, which allows us to choose the model we want to perform classification of spectral readings with. By default, we get the best model chosen by the pipeline, but we are free to choose whatever technique we want, forcing the stages of the pipeline. In the first plot, you can see the marginal probability density function of the top latent variable, which is what is used to actually decide whether a sample is from one evolutionary class or the other. Moving to the right, we have the scatter plot of the top 2 latent variables for the 3 classes. To the right again, we get the plot of the most relevant spectral features grouped by evolutionary class. This concludes our trip to space, And it's time to go back to the ground, or better underground, as we're talking about gas and gas pipes and gas meters. The problem analyzed by the dashboard I'm going to show you is the detection of anomalous gas consumptions both in households and businesses. The remotely sensed data is therefore the actual consumption reading that the gas meter records and sends daily to the IoT hub. The number of meters is in the order of the millions. On top of these readings, we train neural models to predict whether a reading is anomalous and whether the meter is faulty or not. The dashboard you are seeing in this slide is what we call business intelligence view, which allows business people to quickly understand the status of their domain without sifting through millions or billions of records. For instance, in the left widget, you can see the heat map of the regions of the south of Italy with more faulty meters, whilst the other widgets show other business-relevant statistics which allow non-technical people to say whether things are okay or not. The previous slide was showing the BI view, which is a kind of bird's eye view of a domain. It is not always sufficient to show high-level aggregated information, especially when decisions need to be taken, and it is of the utmost importance to know what's going on in a detailed way. This detailed view of data is what we call operational view. For instance, in the context of the same gas anomalies detection project, this view allows to get down to the detail of a single gas meter, showing the user information about, for instance, the single prediction the model made for an household, plotted versus the actual consumptions for the day. In the second box, the one below, you get the view from the sky of the address of the meter, so that it can be seen in its actual context. These kind of details are absolutely vital if a tool like this is to be part of, let's say, the billing process of a gas provider. This concludes our tour of dashboards for remote sensing data, and I hope it's been interesting, and I really thank everyone for the attention and hope everybody has a good evening. Thank you, everybody.